Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Chris, part 3 in our favorites. We're back to you. We're back to a Chris Bolhe's favorite. What is this episode? Why is it your favorite?
You kind of have a theme with your picks, and so do I guess, at least in these first two, because the first one was carbon, the misconceptions, and this one is the age of the Earth or how to build a planet. And we just we didn't know which title to go to, so we just threw them both in.
Just combined them.
So I love this episode.
Throw them together.
So I love to talk about things like this. I love to talk about things that are important to other people, no matter which way they believe in terms of age of the Earth. And I hate to say the word believe because I don't think that that's what this is, but I still love to engage in important discussion. And I think that this episode is a part of that. What do you think?
I think that's right. I love this episode for that reason. I'm less exposed to sort of the discussion about the age of the Earth, let's say. But what I did like about this episode is we really got into the question of what is the age of a planet? How does a planet actually form? It's a long process. It takes a long time. So actually definitively saying what is the age of the Earth didn't just snap into appearance, right? It got built up over millions of years, tens of millions of years even. And so that was part of the interesting discussion for me. But yeah, I agree. This is a completely, really important episode and kind of gets into your passion of astronomy and planetary science. It kind of bridges in that direction, right? So I liked that aspect too.
Lots of good things. Well, Jess, what do you say? Let's get to it.
Let's do it, man. Let's get to it. All right. Christopher Balhuis.
That's that. Yeah. That when somebody says that on the phone, that's when I hang up.
This is going to be a great exercise in Chris keeping Jesse out of the weeds. I think
I'll do my best. I apologize right now. I'm gonna try.
We're talking about the age of the Earth, and this is near and dear to my heart. So I don't even know where to begin, Chris. Like I don't know, where are we beginning here? You could maybe start by keeping me out of the weeds.
Okay. We're just going to go ahead and jump right into the episode is how old is the Earth? And we're going to get into how do we know this? And I mean, this is what you do. And you've done this for a long time now. So you are definitely the expert in the room. I'm really looking forward to this episode. I mean, because it's an important topic.
Yeah. So I think a lot of people know that the Earth is 4.5 billion years old, roundabout, right? And people kind of know that number roughly. Some people might say 4, some people may say 5 billion, something, right? Would you agree with that for the most part?
But they don't know how we came upon that number. Like, how was that done, right? And that's what today's all about.
And then there's also a couple really interesting questions in that because people assume, oh, that's the age of the Earth. And then, oh, that must be the age of the solar system, probably too. And those are two very different things. And we know them to very different levels.
However, what you just said, first of all, I don't agree that most people assume that the solar system is the same age as the Earth.
Okay.
I don't think a lot of people have that connection. And also, you always are quick to point out that they're two really different things. However, I want to say, and this is really a big part of our episode today, is how actually things in the solar system and how the solar system forms plays into how we got the number of how old the Earth is.
That is exactly right. So, Chris, the question we have to start out with is, how old is the Earth? And so what is that? When did we figure this out? Give us a little intro to the history of this.
So it all happened around, or not really around, 1955. Up until that point, we really didn't know. I mean, some people thought it was 1 billion years old. Some people thought it was 6 billion years old. But then we used techniques and methods that were developed during the Manhattan Project. And I think most people are familiar with the Manhattan Project, the development of nuclear energy, right? The development of nuclear bombs. And we really honed in on uranium to lead. The decay of uranium-238 to lead-206 and uranium-235 to lead-207, we really, really honed in on those rates of decay. And we also used the same elements, or isotopes, I should say, in meteorites during that same time.
Yeah, and this was the real revolution in nuclear weapons and using uranium for nuclear weapons and nuclear energy, is that we really got to understand how those two isotopes, uranium-238 and uranium-235, the two flavors of uranium, how those decay and break down and end up in lead. And then this is a massively useful tool for my life today in geochronology. I mean, that is what we measure in the lab, uranium and lead. And those two things are clocks, and we can use those two clocks together, leverage them against each other, and measure ages. And so what people did in this time period...
Those two clocks, I'm sorry, I got to interject. Those two clocks run at different rates, and they run independently of each other, which is hugely important. So we can like cross-check using those two clocks.
Yeah, and if you want to have a more detailed rundown, I don't think we're going to get too much more into detail about uranium lead today, Chris, but if you want to have a more detailed rundown, we've covered this before in the Ancient Nukes episode of, I don't know, probably a year and a half ago, maybe something like that. So go back to that. We cover how nuclear reactors work and some really cool stories about that, and get into the details of uranium and how it breaks down to lead. But in 1955, after around about a decade of work, a research group led by Claire Patterson determined the age of the Earth. And I'm going to throw some numbers out here, Chris. You said before we didn't know at that point in time whether the Earth was 1 billion years old or 6 billion, somewhere in there. That's a pretty big range. They determined the age, huge range. They determined the age of the Earth to be 4.55 billion years old. So that's 4,550 million years, plus or minus 0.07 billion years. So 4.55 plus or minus 0.07. So that 0.07 billion years, that's a 70 million year uncertainty, which is a lot.
Okay, I got to put this in perspective. 70 million years is a ton of time. 65 million years ago, our planet got hit with a game-changing meteor. That was 65 million years ago. That's the time that the dinosaurs met their extinction. So we're talking about a plus or minus here in the age of the Earth that exceeds that difference. That's a lot of time. Now, Jesse, you and I, like, we're used to dealing with numbers that are in billions and millions, and I think we get desensitized.
Well, first, let's consider that before this number, we're going to kind of rip on this number a little bit, but before this number, we had a range between 1 billion and 6 billion, which is a huge range. Basically, we had no idea. Now it's 4.55 plus or minus 0.07. So a lot better. But let's put this into some real life context. The average American lifespan is around about 79 years. So if we shrink the age of the Earth down to 79 years, that uncertainty, 70 million year uncertainty at 4.5 billion years ago, is basically like knowing when you will die down to the closest 1 year, 2 months, and 12 days. So that's like saying, I'm going to die 79 years from the day I was born, but I might die 1 year, 2 months, and 12 days before my 79th birthday, or I might die 1 year, 2 months, and 12 days after my 79th birthday. So you kind of have an age range of 2.5 years. So you might die on your 79th birthday, somewhere within 2.5 years on either side. Does that make sense?
It does. It makes great sense, actually. And I'm a little conflicted by that. Like, I am, because a part of me is like, wow, that's pretty good.
Yeah.
But then the other part of me is like, well, that sucks. I don't know where to go.
No,
like,
I don't, and actually,
honestly,
I think it's better for me personally, it's better if I just don't know when I'm going to die. I think for my mental sanity, it's better.
I was just going to say that the interesting thing is that we have not improved on the age of the Earth since that time. 1955, we've really, like, what the hell, Jesse? What's going on?
So our methods, just to kind of give you a sense of how much our methods have improved, that number, 4.55 plus or minus 0.07 billion years, that took years to develop the lab techniques in order to make those measurements. They were reproduced in multiple labs, so it's a solid number. Our lab at Penn State, we don't do the exact same stuff, but we can make an age measurement with the uranium lead system in 45 seconds. So we can do hundreds of analyses a day. And so our lab techniques have improved massively since 1955, as you would expect, right? But you're exactly right. Our understanding of the age of the Earth has not really improved since then. I could talk about this in what we know, what we do know, what we have improved upon. In the Earth's oldest rocks, some of which I studied during my PhD, are 4.0 billion year old rocks. And we know the age of those rocks to plus or minus 800,000 years. So that's 4.030 billion years plus or minus 0.0008. So much
That's
better.
Really accurate. Yeah.
Very accurate,
gosh.
very precise. That's a solid age. There are some rocks in northern Canada that people have suggested are about 4.28 billion years old. Now, there's a bit of debate about that. I sort of generally agree with the idea that those are old rocks, but there is some debate about whether these rocks are actually 4.28. So the oldest accepted aged rocks are 4.02, which is 500 million years younger than the Earth. And that's 1/9 of Earth history. And that's almost as much as we've had multicellular life on Earth. So this is a huge age range. Like, this is a massive amount of time. So we do have very old pieces of Earth, though, that are not rocks. We have actually what are called detrital mineral grains. So these are zircons. It's a certain mineral that is eroded and deposited in beach sands. We have individual zircon grains that are 4.38 billion years old. Now, those zircons crystallized in a magma 4.38 billion years ago. That rock then got eroded and deposited in older sediments. So we don't have the rock itself, but we have little tiny fragments of the rock. And those are the oldest pieces of Earth, which are still 200 million years younger than the Earth. And so this kind of begs the question, how do we know the age of the Earth? And so I need to go back to that 1950.
Well, okay, Jesse, I got to interject a second then, because I think I need you to do this because you're the expert in the room and I know the answer to the question, but I'm going to ask it. What starts the clock, or what can reset the clock? Because you're talking about ages that are in the oldest possible grains, those detrital grains of 4.35 billion years. That still doesn't get us to 4.55 billion years. So what resets the clock? We need to talk about that first.
Yeah. Absolutely. Great question. What resets the clock depends on what type of material you are looking at. For individual grains, it's either heating them up to high temperature or melting them, recrystallizing the grains. With a rock, basically mostly any kind of really high temperature metamorphism or melting. So if you melt a rock, it resets all the clocks in there, and you basically reset the chronometers, flip the sand dial over and start it again. So this kind of begs the question.
Can you explain that a second, though, to Joyce, my mom?
Yeah,
why does melting a grain reset the clock? You got 30 seconds, go. Why does that happen?
Yeah, these particular grains are very useful because they have a lot of uranium, no lead. And so any uranium that starts there decays away to lead. Most of the lead that we see in the grain is by radioactive decay, which means it's a very accurate and precise clock. As soon as you melt that grain, all those uranium and lead atoms from that grain mix back in with the magma, get mixed up again, and the new grain grows, and it grows with a lot of uranium and no lead again. So it kind of overprints this clock. It's just like the sand dial. The sand in the top is uranium. The sand, as it trickles down, is turning into lead at the bottom of the sand dial. When you melt it, you flip that thing over. You just have uranium in the top and the sand is down in the bottom. It starts to fall back down into the bottom. So you basically reset this entire clock by removing the product or the daughter isotope, the lead in this case.
Hey, well done. I liked that. You've never busted that one out before.
Well, thank you.
I don't think you've ever done the little sand dial thing.
The sand dial one?
Joyce, I think, can understand.
Well, there we go.
Joyce gets it.
Okay. All right. Yeah. Well, good on you, Joyce.
Nice
I'm glad.
Job. I like it.
So all this conversation kind of begs the question, how do we know the age of the Earth? Like, where did this 4.55 number come from? So I'm going to spend, again, 30 seconds on that really quick, Chris, just to get us level set here.
You've gone over your allotment, so hurry up.
Okay. All right. I'm over time.
Let's go.
So this 1955 age was basically doing uranium-lead geochronometers, except comparing the Earth, the crust of the Earth, the mantle of the Earth, to the core of the Earth, except it wasn't the core of the Earth because we can't sample that. It was using meteorites to sort of predict what the core of the Earth would look like. And so if you use uranium-lead chronometers on the crust, the mantle, and the core, you get an age, basically a planetary, what's called a planetary isochron. But you get an age for the entire Earth for this, and that gives us that 4.55 plus or minus 0.07 billion year number, which we have not improved upon since 1955. But Chris, I've described how we made the age of the Earth measurement. I've described what we know about the oldest rocks and minerals. Why do we not know more about the age of the Earth since 1955?
Well, the Earth doesn't have any original rocks. It doesn't have any rocks that exist at the surface that are going to be 4.55 billion years old. And that has to do with, well, perhaps the most famous event that happened is the forming of the moon. Okay, our moon. And this happened when a planet that's the size of Mars, so roughly half the size of Earth, collided with Earth between 4.5 and 4.35 billion years ago. So early on in the formation of planet Earth, there was just this devastating collision that happened. So what happens when something like that occurs? This event is so big that the entire surface of the planet is resurfaced. In other words, it melts and then begins to cool. And like you said, and we already hit upon this is why I asked the question earlier, is that when you melt rocks, it resets the clock. So if that event happened 4.35 billion years ago, no rocks will show an age older than that.
That's right. Just a planetary resetting event right there. Just completely overprinted almost the entire planet.
Which is super interesting because we know that this happened as many as 8 times, actually, where Earth was just blasted during a part of our formation, which is called the heavy bombardment era, where we got blasted with such big impactors that it resurfaced our entire planet. When an object the size of Mars slams into us, that's a massive ordeal. And so that's why we're never going to be able to improve upon the age of the Earth with Earth-based rocks. So we have to look then to other things. And so, Jesse, let's talk about meteorites then. We have big meteorites. We got little tiny meteorites all the time that are adding mass to our planet. What do they say in terms of age? Because when a meteorite forms, nothing really happens to it after it forms. There is no resetting. So the age we get is the age that thing formed.
Yeah, there's no plate tectonics on most meteorites. This overprinting that happens on Earth all the time, this resetting of clocks, of rock clocks all the time. So there are tiny parts of meteorites, the earliest bits. We can date many different stages of meteorite formation, from melting, the first melting to core formation to the first solids that formed in the solar system. And the most primitive ones, the first solids that really condensed in the solar system, give an age of 4.5682 billion years, plus or minus 0.00017 billion years old. So let me say those numbers a little bit differently. That's
crazy.
It's incredible.
I want everybody to listen up because this is amazing.
I'm going to say these differently. This is 4,568.2 million years, plus or minus 0.17 million years. So that's an uncertainty going back 4.568 billion years ago, an uncertainty of 170,000 years. So that's plus or minus 170,000 years. So let me put that into our age of a human being context, Chris, here, is that we were talking about a lifespan of 79 years. You would know it to plus or minus 1 year, 2 months, and 12 days. This one, if you have this precision in your life when you're going to die, you're going to know that you're going to die on your 79th birthday. You're going to actually know the day you die to within one day in 1.5 hours. So that's, you might die on the day before your birthday or the day after your 79th birthday, but you're going to die one of those 3 days, right? That's spectacularly precise. That's incredible.
Yeah, it is incredible. And again, it's important to highlight two things with this. That's how precise our methods are. I mean, this is what you do. It's exceedingly precise. Okay. The other thing is, why are we able to do this with meteorites? And I know you said it. I want to come back to it because it's such an important point. Meteorites, nothing happens to them. They form and they don't get remelted ever again. But on Earth, Jesse, you as a guy that dates rocks, dates old shit, you have to have a love-hate relationship with plate tectonics then.
Yeah.
And your rocks, because plate tectonics is what makes this an amazing planet. It's what makes our planet so beautiful, but it makes it so difficult for you to do your job because it constantly recycles rocks. And so we got melting, we have metamorphism, which can reset clocks depending on what method you're using. It adds a lot of complexity to your job.
Very frustrating sometimes. Absolutely.
And you don't get that with meteorites, which is why we're able to use those and get a better approximation of the age of the Earth.
And that really brings up the main question, I think, here, Chris, which if you're sitting there listening to this, alarm bells should be kind of going off in your head, right? You should be thinking, okay, we can know the age of meteorites really, really precisely, but we haven't improved on the age of the Earth since 1955. You should be going like, well, how does a planet actually form, right? I mean, I think that's like the sort of natural follow-on to this is like, what the heck does the age of a planet actually mean if the Earth, the proto-Earth, got hit by this Mars-sized impactor and totally reset the planet? Like, what is the actual age of the Earth? So, Chris, let's wrap up this episode on that theme. We got to start a little bit earlier than a planet, though, first to kind of get to this, right?
So this is really difficult, Jesse, to talk about, the formation of the solar system in a couple minutes is a tough task. But look, it all comes down to what's called the nebular theory, the solar nebula theory. And the idea is that our solar system formed from a nebula, this cloud of gas and dust that was contracting due to its own gravity. And, you get the formation of the sun, and then everything else in our solar system, the planets, the Kuiper belt, the asteroid belt. And the idea is that as it started to contract, as this nebula began to contract, it began to spin and to rotate. And, you and I were talking about this earlier, and it's kind of like somebody taking a ball of dough, like pizza dough, they roll it into this ball. And what happens when you take that ball of dough and whip it into the air and rotate it? What happens to it?
Yeah. You get it flattened out, right? You can picture the person in the pizza parlor, throwing the dough, tossing the dough up and spinning it out into a pizza shape, right? It's kind of what's going on here in this collapsing cloud of gas and dust. And then the next thing happens, which is the star ignites, which starts to produce a lot of heat. And that basically moves all of the stuff that has a low condensation temperature, meaning it likes to be in the gas phase. Think CO2 or water and hydrogen. That all gets kind of pushed out away from the star, kind of gets blown out until it gets cool enough for that stuff to condense. That line defines that's called the frost line or the ice line in some textbooks.
The condensation line is what it's called.
Exactly. Yeah. It's basically the freezing point.
The condensation sequence, yeah.
It's basically the freezing point in the solar system. And the inner part of the solar system will be what we call the rocky planets, the ones made of mostly rock. The outer ones will be the gas giants, the ones made mostly of gas, like Jupiter and Saturn in our solar system. And so, as this dust cloud, now this is mostly rock dust now, those little dust particles will electrostatically cling together and form larger dust particles, and those will get a little bit larger, and then those will get a little bit larger. At some point, they'll reach a stage, something larger than the pebble size, where they start to have their own gravity. And then they'll start to attract each other. And then you can get one big one that has more gravity, attracts more little ones, which makes it bigger, which means it has more gravity, which attracts more little ones, and it grows exponentially. And this is this runaway growth phase, which basically starts to build a planet.
Eventually it becomes a planetesimal. Gets to this certain size where it begins to grow due to its own gravity. It begins to draw things in from outside. If it becomes a planetesimal, then astronomers say, well, then it's destined to become a planet. And this is what really never happened to Pluto, for instance. A lot of people get emotional about Pluto getting demoted to a planetesimal instead of, or to dwarf planet, I should say, instead of a planet. Well, one of the criteria that we have set for something to be classified as a planet is it has to clear its own orbit. You know, it has to clear out the vast majority of the debris in its orbital plane. Pluto hasn't done that. There's a ton of stuff in its orbital plane. And so I just want to say that, like, if this is how it happened, you take this ball of pizza dough and spin it in the air, how does that tie into our solar system? Well, there's a bunch of stuff. All of the planets are revolving in the same direction. And they're all revolving in the same plane, too. I mean, it's a very, really small variance in terms of the plane at which they orbit relative to the sun. All but Venus and Uranus rotate in the same way. Everything rotates counterclockwise except Venus and Uranus. All the moons revolve and rotate counterclockwise. These are also predictions that are based on this solar nebula theory. And sometimes in science, Jesse, like, I think you'd agree with this, sometimes the predictions become more important than the theory itself.
Yeah, exactly. Those are the things that become testable in the future. And those are the things that you can go forward and test. So you nailed it perfectly there, Chris. And this leads us really perfectly to, what does the age of a planet mean? Because this process we're describing is potentially a long process. This could take a while. And so there's a couple other key parts here, and I'm going to put some numbers on some things. So as this planetesimal gets big, in the early solar system, there's lots of radioactivity around. There's a lot of stuff. Think of like a nuclear meltdown, Chernobyl. The reason why nobody can really live by that thing is because there's so much radioactivity around there. That's the same thing that was going on in the early part of our solar system. Loads of radioactive elements, all decaying away, producing heat. When you get this planetesimal size, you have a lot of heat inside that can't escape quickly, so the planetesimal melts. That melting event means that you can start to form a core, and the core formation is what some people consider to be really like a planetary age event. That is this melting that can reset the clocks and can give you this 4.55 plus or minus 0.07 billion year old age for the age of the Earth. Now, that process can take a while. The core formation process on planetary bodies the size of Earth in our solar system kind of is around 30 to 80 million years after the start of the solar system. So this whole process we've been describing from nebula theory forward takes about 30 to 80 million years. There's some disagreement about that, but it's kind of in that range for the most part. And the Earth is thought to be about 50% of its current mass by that age range, 10 to 50 or 60 million years after the solar system formed. So that's about 4.5 billion years old.
And that's why then meteorites date that same time frame older than Earth, because Earth took time to cool. Whereas meteorites, being much smaller, they cooled much faster, right? And so their age is going to be really indicative of the age of the solar system. Whereas Earth is going to be a little bit younger than that. It's kind of like this. If you take a coffee cup and fill it with hot water and let it sit on the counter, and you heat it up to like 104 degrees, the temperature of a hot tub, but you compare that to filling a whole hot tub up with 104 degree water, and now just let them both cool. Turn off the electricity, let them cool. The cup of coffee is going to cool much faster. In terms of like age of rocks, that cooling faster, turning it to rock sooner, means it's going to show up as being older. Even though they like formed at the same time, the clock is going to be older. than the clock of Earth. Does that make sense?
Yeah, absolutely. And Earth is still warm. It's still melting. There's still a lot of heat inside of Earth that is melting, and so it still hasn't cooled down yet 4.5 billion years later.
That's right.
So
which is why Earth still has plate tectonics. Mars is, volcanically inactive. It's cooled off. It's half the size of Earth. And so there's very little activity going on there. Mercury, same thing. Now, look, I'll eat my desk in front of me if Venus does not have volcanism on it right now. I'll eat it. I'll eat the whole thing. Okay. That's how confident I am saying it, because Venus is about the same size as Earth. And so it hasn't cooled off yet either. It's still an active planet, and it's going to have volcanism then because of that.
Oh, I can't wait to see what these missions to Venus end up returning, because it's like the most interesting data point in our solar system is how does Venus compare to Earth? So, Chris, this is sort of a wrap on the information, but I just want to kind of summarize here. Like, there's a few key take-home points. First of all, the age of the Earth is about 4.55 plus or minus 0.07. We've said that number a whole bunch of times, and we haven't improved on that since 1955, and we kind of discussed the reasons why. We know the age of the solar system much, much more precisely than we know the age of the Earth. And that's point 1 and 2. And that brings us to point number 3, which is building a planet is a long, complicated, and often violent process. And that's really why we don't have a great idea of the age of the Earth specifically, but we know the age of the solar system very precisely.
Yeah.
That, I think, is a wrap, Chris. This was really fun. I just said, it's near and dear to my heart. I hope I didn't blather on too much and spend too much time down in the weeds about it.
No, you do such a good job.
It's really interesting. I think it drives home a couple really important points about, how a planet forms, and put that 4.55 number into some context for people. At the next dinner party, which everybody loves talking about the age of the Earth at dinner parties, right? You can pull out
Joyce
this little
is well
fact.
Equipped right now to go.
Totally.
That's right.
She's going to be rocking it at the next dinner party. Oh, man. All right, dude.
This is going to be a true test to see if she listens to our podcast.
That's right. So. That's right. You're going to get like a phone call and a Facebook comment from your mom. That'll be great.
That's right. That's right.
All right, man. Well, you can follow us on all the social medias at Planet Geocast. Send us an email. We love hearing listener questions, and we love interacting in that way. Our website, planetgeocast.com. Check it out. There's some really funny and excellent pictures of Chris Bullheis in there. And give us a rating, review. That stuff really helps the algorithm. We love that.
Yeah, but the most important thing is to share our podcast with somebody else that loves our planet.
Or somebody else that doesn't and should. That's okay, too. You can harass people. Feel free to harass people.
Good point.
Say, hey, listen to this. You need to know more about this.
Yeah.
Try this. Try these idiots on for size.
That's right. That's right.
All right.
Cheers.
Peace.